line, the tangent line. So we've essentially taken this idea of instead of pointing this direction and trying to find that up and down or this direction up and down, we're pointing in an arbitrary, well, not arbitrary, it's an angle of pi over 6. What's our up and down that direction? All right? And we can do this now for any angle that we want. Right? We can point in any direction and start walking. Let's see what the next one looks like. If z equals this function of two variables, then find the directional derivative at the point 2, 1 in the direction of the vector u equals negative 1, 2. So you help me out here. What should we do first? So we what?
I'm just keeping track of what we have already. We already have the equation. We have the direction vector, and we have the unit vector, and we also have a point. So
we don't have the unit vector, right?
Yeah.
Do we have the unit? I thought u was the unit vector.
Yeah. But if you take the length, it's not 1.
It's not 1. So I'm trying to trick you on purpose here. So that u, even though I called it u, is not a unit vector. And to use the formula, it has to be a unit vector. So we have to recognize that when we look at it, that's not a unit vector. So we can always check its length, right? Let's see, what is the length of this vector? It needs to be 1. It's root 3, and that's not 1. So that's okay, because I can still find a unit vector that's in the same direction as that one, right? So let's call it, instead of u, let's call it v. V is going to be the vector that points in the same direction as that one, but will have a unit length. And that'll be just each component divided by the length of the vector. Pardon?
Wouldn't that be root 5?
Yeah, it's root, I don't know. I heard root 3. I wasn't thinking when yeah, okay, 5. Root 5. Yes?
Yeah.
Okay, so now we have a unit vector that points in the direction that we want to be pointing in. We still need partials, don't we? Like we're going to need partials for this. So let's go ahead and take care of that work also. What's partial of f with respect to x? Derivative natural log of something is 1 over it, right? And then plus, then times the derivative of what's inside, which is just 2x, and I'll just slap that on top. And then the partial of f with respect to y is the same exact thing with 2y on top. So there are your partials. And so let's go ahead and write down everything we want here. We want the directional derivative in the direction of the vector v, because we're not going to use u, we're going to use v, of the function at the point 2, 1. All right? That's what we want, right? And this should be equal to a, which for us a is this piece, negative 1 over root 5, times the partial of f with respect to x evaluated at 2, 1, plus b, which is 2 over root 5, times the partial of f with respect to y evaluated at 2, 1. So we still need to do those evaluations, don't we? So what is this one? 2 for x, so 4 on top, and on the bottom we get 5, 4/5. And then what about partial with respect to y at 2, 1? 2/5. So this is negative 1 over root 5 times 4/5 plus 2 over root 5 times 2/5, which at the end of the day is 0. Isn't it? Which means what?
Well, it's flat in that direction.
Yeah, in that direction, I have no rate of change, no increase or decrease. Now that doesn't mean that I'm at a top, right? That doesn't mean that I've hit like a peak of a hill. It just means in that direction there's no rate of change. You can think of it like this. I mean, if I take this piece of paper and I fold it up like this, right? Like in a parabola, right? Then if I'm on this surface and I walk along that bottom edge of the parabola, right? Then I'm always going to be flat, right? But if I go in any other direction, I'm going to be going up. So just because your derivative is 0 does not mean you're at a maximum or minimum, right? Does that make sense? Okay, so we will be asking ourselves then, what do we need to be able to say we're at a max and min? That's coming. We're not there yet. All right. All right, so this is a really, really important part of what's about to come. So want us to notice something about that formula for the directional derivative. Okay? Notice the way this is written. Do you agree that it could be rewritten this way? Like I could take this vector right here, which the first component is the partial of f with respect to x. The second component is the partial of f with respect to y. That's my first vector. If I tell you to dot that with this vector, you would do this times this plus this times this, and that would be that, right? So the directional derivative can also be looked at as a dot product. If we wanted to, right? And you might be asking yourself, why would you want to do that, right? But just agree with me that you could, yes? And that vector AB is that unit vector. So this is a very condensed notation for the directional derivative, right? It's this thing dotted with that unit vector. Okay. So what, right? Well, before we proceed, let's use a special notation for that vector. That vector right there, right here, this thing that we just kind of made up out of nowhere, we're going to call that something. That vector right there, we're going to call the gradient vector. Okay, so this is a new definition. We define the gradient vector to be, this is our symbol for the gradient. The gradient of our scalar function is just the vector that is created by taking the two partials and putting them together in a vector. Okay? So we're just going to say, hey everyone, that's now called the gradient vector. All right? All right. So well, let's do this one. Keep that on the back burner. We turned this thing into a dot product, right? And we were like, why? Just back burner that for a second. Let's do this example. Just want to make sure we understand what this is asking. So find the gradient vector for this function. So that means we want to find this, right? Which by definition is this. It's just a vector that we create that's going to have the two partials in it. So what is the partial of f with respect to x? This one's a little tricky. What is the derivative of e to the xy with respect to x? So what's the derivative of e to anything? Itself, right? E to that something. And then times the derivative of what's in the exponent. So what's the derivative of x times y with respect to x? Just y, right? So that's the derivative of this with respect to x. And then the derivative of this with respect to x, which is minus sine of x plus y, right? And then what's the derivative of what's inside of here with respect to x? 1 plus 0, so just 1. So that's it, right? That's the derivative of f with respect to x. Okay, comma. Now the derivative of f with respect to y. Again, e to the xy, but this time times x instead of y. And then what about the second part? Same thing, minus sine of x plus y. And then close this off. Okay? This is the gradient vector right here. That was just practice to make sure we understand how to calculate the gradient vector. Now, before we see the beauty of this and that turning thing into dot product, let's just extend the idea out. What if we had a function of 3 variables instead of 2? Then what if we had a vector, a unit vector u, right, that now has 3 components? Then the directional derivative for that function of 3 variables would be a, b, c, the 3 components, times the 3 partials. See, now we have 3 partials with respect to x, y, and z. And therefore, the gradient vector will be 3 components, right? The 3 partials. Now, what's difficult about this is that I can't visually explain this to you as well. Because instead of me saying, okay, you go, x and then y, and then you go up to the surface and you point in a direction and slope a tangent line, can't do that anymore because now it's like the x, the y, and the z get plugged into a function. So now you're in 4-dimensional space and you're pointing in a direction, a 3-dimensional vector, so that can be, yeah, we can't visualize it anymore. But the ideas are all still here. Now, what do you think? What do you think the dot product in there is going to be used for? I mean, what do you think the most important thing? What do you think the most important aspect of the directional derivative is? Like, what do you think we would want to know?
Can be applied at any point.
It can be applied at any point, but like, let's say you go to a point. What do you think you'd want to know once you get to that point?
Which
What?
direction you're facing?
Okay, well, that's kind of. Okay, so right now, if I tell you go to a point, we can point in a direction and we can figure out the slope right there, the rate of change.
The slope in every direction?
That'd be a lot of them.
I mean, like, that's what we
Where's
want
the
to know.
steepest slope?
Would that be it?
Where the steepest slope would be?
So if I give you a point in a direction, you can tell me the slope. But what about asking the question, if you're at a point, what direction gives you the steepest slope, right? So imagine you're on a surface, and you're sitting there, you know that, okay, if I point here, I can get a slope, point there, I can get a slope, point there. Great, you can point in any direction and get a slope. But what about you telling me which direction I should point to get the most slope, instead of, giving you directions and you calculating slopes? Does that make sense? That would be more useful? Okay, well, remember that when you have a dot product of anything, right? You take the dot product of any 2 vectors, that it's the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between the vectors, right? Right? So remember, we rewrote the directional derivative as the gradient dotted with the unit vector, our direction vector. But if we rewrite this using that, then the directional derivative, this, remember, represents the slope of the tangent line, right? This right here is a number. This is the magnitude of that times the magnitude of that times cosine of the angle between them. But that's just that. Why is this? Because that's a unit vector, remember? So that's just this. And now you look at this and you ask yourself, what would I need to make this the biggest it could possibly ever be? What would make this the biggest it could ever be? Is if this angle was 0. Because cosine of 0 is 1, right? Understand that? But what does it mean to say that this thing is 0? It's saying that the angle between what is 0? The angle between these 2 vectors needs to be 0, right? For you to get the maximum rate of change, so again, I'll walk out, x value, y value, I'm standing there and I'm asking, which way do I point? Which way do I point in order to get the steepest rate of change? The answer is that you need to point in the direction where the angle between these 2 is 0. which means that the direction you point is actually the gradient vector itself. Wait, yeah, that should make you say wait. Look, in order to get the steepest descent, the direction I point in needs to have an angle of 0 with the gradient. So look, do you agree that the gradient vector is set? It's set in stone because it comes from the function. So when I go and I walk and I get to a point, there is a direction vector given to me by the, there is a gradient vector already there, right? It's already there. I have no control over that. This is telling me that, guess what? In order to get the steepest rate of change, I need to point in the same direction as the gradient vector. And then you will be getting the steepest rate of change.
The gradient vector is the steepest?
The gradient vector will always give you the direction of the steepest descent. Okay? And the magnitude of it is the answer.
Yeah.
Because look, the magnitude of the gradient vector, if that's 1, that's the biggest it could ever be. The magnitude of that is going to be the biggest directional derivative we can get. So the gradient vector, in other words, is super important because it gives you not only the direction of the maximum rate of change, but the maximum rate of change at that point. The maximum value of the directional derivative is the magnitude of the gradient vector and occurs when we point in the direction of the gradient vector. That's the big kaboom idea here, all right? So let's say we have this surface. Then find, first of all, the direction of the maximum rate of change at 0, 0. So we walk, we don't go anywhere. We plug 0, 0 into the function, we're standing there, we're up there, we're looking around, we're like, okay, which way do I point to get the maximum rate of change? And then tell me what that maximum rate of change is. So how are we going to determine that? For part A, we just need to figure out what the gradient of f is, right? At the point 0, 0. Right? That's going to answer part A. Now, we're going to get a vector as an answer. And they want the answer as an angle. All right? And that angle relative to the x-axis. All right? So let's compute the gradient. What is the gradient of this thing? The gradient of f is equal to the partial of f with respect to x, partial of f with respect to y. Okay? I don't know. I mean, I've been teaching this for a long time, and every time I cover this, it just continues to blow my mind that seems like a very difficult question. Give me an arbitrary surface. Take me to a point on that surface that I can easily tell you which way you should point to get the maximum rate of change. It seems like it should be harder than that, right? But it's not. So long as you can compute the gradient, let's see. Can we get the gradient on this? Partial of f with respect to x. So derivative of sine of something is cosine. And then what's derivative of what's inside of that with respect to x? Just 1, right? Okay, plus derivative of cosine of x with respect to x, which is negative sine x. Okay, so that's the partial of f with respect to x. Now, what's partial of f with respect to y? So derivative of sine of something is cosine of that. What's the derivative of what's inside of here with respect to y? Negative 1. Be careful on that one because you're taking derivative of both of those. That's 0, and then that's minus 1. And then plus what? 0, right? Because cosine of x is a constant. So that's it. That's your gradient vector, right? That's your gradient vector. Now, we need to know the value of that gradient vector at 0, 0. So now I'm going to plug in x is 0, y is 0, and see what I get. So the gradient vector of f at the point 0, 0 should be, let's see, 0, 0. Cosine of 0 is 1. And then minus sine of 0 is still 0, so there's 1. And then cosine of 0 again. And then times negative, so negative 1. There you go. 1, negative 1. So let's try and visualize this looking down. You know what, I'll do it this way. If this is x and this is y and this is z, we have some surface up here. We're standing here, we plug in 0, 0, we go into the surface, we're somewhere up here on the surface. And it's saying, okay, which direction do we point in to get the steepest descent? It's telling us to point in the direction of this vector. So let's draw that vector on the ground. You go out x1 and you go y negative 1, right? So x1 would be this way, 1, then y negative 1 there. So you're going to point in that direction on the ground, right? What is that as an angle? I think it's pretty easy to see the angle. Is it not easy to see that angle? Relative to the x-axis. 45, but into the fourth quadrant. So like maybe negative 45 degrees, or if you want, you could say like 315, right? However you want to say it. You know, looking from the top down, x, y, we are here, right? There's 1 and there's negative 1. So we're there, right? Looking from the top down. So the angle, the direction as an angle is negative 45 degrees, you know, relative to the x-axis. So again, I can't help but see myself standing here, 0, 0, I'm up here on the surface. Okay, which way do I point? X-axis, y-axis, right? Which way do I point? 45 degrees this way, right there. Take a step. In that direction right there, you're going to get the steepest descent. No other direction will get you anything steeper. Now, how steep is it? So part B. How steep is that? Well, it's the magnitude of the gradient vector at 0, 0. So it's just the length of this vector, root 2. That's it. It's amazing. Same problem, I mean, same idea here, right? Same two questions. Although the part A is not asking, oh no, it does ask as an angle. So let's do this one. So if you kind of take a step back and look, like today, the beginning of the section was like, hey, look, take me to a point on the surface, point me in a direction, tell me the steepness. Great, that's fun, you can do that, but who cares? What's really important is take me to a point on the surface, tell me which way to point so it's the steepest, right? This is the more important topic here. All right, so part A, what do I need to calculate? The gradient at 1, 2, right? This is what I want. I want the gradient of this function at the point 1, 2. So let's first get the gradient, which is the vector, which is the partials. And that is, let's see, are these partials easy? Oh, these partials are easy, aren't they? So 2x, and then the other one's negative 2y, right? Think that's about as easy as it gets in terms of partials, or no? Okay. Is it? Oh, it is x. Yeah, I'm sitting here saying it's easy. Yeah, it is so easy, it's hard. X negative y, right? All right, so that's the gradient. Now we need it at 1, 2. So the gradient at 1, 2 is 1, negative 2. Okay. Now that's not as easy to get the angle from, because when it was 1, negative 1, we could kind of visualize that that was negative 45 degrees. So for this one, I'm going to draw it. Here's my x, here's my y. I'm going to the right, let's say 1 here, and then I'm going down 1, 2, like this. Okay, so that's the vector. Let's find the angle, this angle relative to the x-axis. Negative, what? 60, is it? So draw a little right triangle here. Wouldn't this side be 2? Like as a magnitude, that would be 2, right? And then this would be 1. So how can you recover the angle out of that triangle? Yeah, you're going to need a tangent function, arctangent on your calculator, right? We know that tangent of theta would be like opposite over adjacent. So that means theta is going to be arctangent of 2. Go ahead and do that on your calculator, and let's see what angle you get. Make sure. Let's see it in degrees. 63 point what? 4 degrees. Okay, now there's a little bit of a problem here because this didn't know what quadrant I was in, right? So we just need to understand that that's 63.4 degrees. So we're going to say negative 63, right? Because we're actually in the fourth quadrant. So negative 63.4 degrees is going to be relative to the x-axis. That's our angle. Okay, so I walked out 1, went over 2, went up to the surface, x-axis, y-axis. I need to point negative 63.4 degrees and take a step. When I do that, I'm going to get the maximum rate of change. And that maximum rate of change is the magnitude of that vector, which is root 5. Right? Magnitude of that. It's just a coincidence that this is 1, 2, and 1, negative 2. You all understand that? Okay. Okay, now this one, let's try and see if we can wrap our heads around this. Because now you have a function of 3 variables. See if you can follow this. Let's just say, for the sake of trying to understand this, that this function tells you the temperature at that particular point in 3-dimensional space, all right? So imagine that I go to the point 1, 3, 0, right? So I'm going to go out out 1, over 3, and 0 means I'm going to just stay there, right? Plug that into this function, and that gives you the temperature. Then what does the gradient vector give us then? So I walk out 1, I go over 3, I'm 0, I'm sitting there on the ground. The gradient vector is going to tell me the direction I should point, right? So it's a 3-dimensional vector this time, right? It's a direction I should point in where I get the maximum temperature change, right? Because the temperature is like a 4th dimension that we can't see it. Right, so let's do it. What's the gradient we need for part A? We need the gradient of this function at the point 1, 3, 0. Right? Oh, shit. I read the problem wrong. Damn it. The first part wants a directional derivative, right? Yeah. Okay, let's just scratch this. I don't care about directional derivative. I want to know the magnitude of the gradient. That's the thing that's most important. So I'm actually going to do part B. So let's find the gradient, and then we'll take its magnitude. All right, that'll be the maximum rate of change in temperature. So what is the gradient of F? Let's start with that. 3-dimensional this time, right? So what is the partial of F with respect to X? Sine YZ. That's a nice one. Okay, how about the partial of F with respect to Y? So that X is just a constant out front, right? X. And then what about the sine? We have to take derivative of it, don't we? Yeah. So cosine of YZ. But then you have to take derivative of what's inside of there, YZ, with respect to Y. So just Z. And then we do the partial with respect to Z. So it's almost like with respect to Y, isn't it? X cosine of YZ times Y this time. So there's your gradient vector. And now we need that gradient at 1, 3, 0. All right, so if we plug in 3 here and 0 here, we get sine of 0, that's 0. What about the next one? Should be 1. And the last one, is it 0? think you get 3, right? Because this is 1, this cosine of 0 is 1, and then y is 3. So you should get 3 here, right? This one's 0. Oh, we didn't account for the z here. Yeah, okay. Yeah, this is 1, and then that's cosine of 0. That's 1, and then 0. So yes, thank you. Oh, wow, that's kind of interesting. For this particular function, if we go out 1 to the point 1, 3, it's telling us that we should point straight up, right? We should point straight up to get the maximum rate of change of that fourth dimensional function. And what is that maximum rate of change? So the magnitude of the gradient of f at 1, 3, 0 would be 3. It's the length of that vector. So again, if that's measuring the temperature of something in three-dimensional space, at that point 1, 3, 0, if we just start moving straight up, you're going to get the maximum temperature differential of 3. Now, I scratched out part A, but how would we have done part A? We would still need this, right? We would still need that, but we would be dotting that vector with a unit vector. And where would that unit vector come from? This right here, right? But we would have to make it a unit vector first. That's not a unit vector. And the train keeps going. All right. Tangent planes. Wait, we did tangent planes, didn't we? We did, but not a final version. So when we did tangent planes at the beginning of class, we said you have to have z as a function of x and y. Right? We said z is a function of x and y. And the formula that I gave you was if z is a function of x and y, then the tangent plane at the point x naught, y naught, z naught would be equal to the partial of f with respect to x at x naught, y naught, times x minus x naught plus partial of f with respect to y at x naught, y naught, and then y minus y naught. And then what was that? That next one I said would always be -1 and then z minus z naught equals 0, right? That was from the beginning of class. That's what we did. This is saying, okay, scratch this. You don't need this anymore. You don't need z to be a function of x and y anymore. You just need an equation that connects all three variables together. So this would work. You remember when we did that one day where I turned the lights off, we looked at all those different quadratic surfaces, cones, ellipsoids, hyperboloids, right? All those different shapes. Those are all equations with three variables in them. We can find the tangent plane for any of those now using this, right? So as long as we can write our equation with our three variables equal to a constant, as long as we can write it that way, so let's say x squared plus y squared plus z squared equals 9, like a sphere of radius 3, right? As long as we can write it that way, then the equation of the tangent plane at any point on that surface is this thing. All right. See that? Doesn't that look like this right there? Except now we have three variables. So when we take the partial, with respect to x, we'll have x naught, y naught, z naught being plugged in. And then this is our little x minus x naught. And this is the second part, right? Like that. And that right there is like that. And then this is the part that was -1 in the previous formula. And the reason it's -1 is because back in this case right here, let's say that I move everything to one side. So take that equation and just move that z over like that. Then if this is your capital F, then when you get to this point right here, what's the partial of f with respect to z? What's the partial of f with respect to z here? -1. every time. Because if you can solve for z, then when you move everything to one side like that, then that derivative will always be -1. All right? So this is a more general version of that. That was a specific case. So these right here are the constants out front. Those basically make up our normal vector for our plane, and that's what this says. If you notice, the gradient of our function, f, capital F, is actually the normal vector of the plane. So that gradient is something else, isn't it? It gives you quite a bit of information. So find the equation of the tangent plane to this. Why don't you work on that? Let's see who can come up with it. So what I want you to do is come up with the equation and then multiply all those coefficients through and get a final equation. All right? And let's see who can come up with it. And I'll give a 2-point bonus on the midterm for the first person who can get this. It's only 2 points, but hey, it's 2 points, right? I better work it out so I know what the answer is. Just bring it up to me when you have it. Got it? Okay, good. Good. Put your name on, or yeah. Yeah, you know what, let me put something on here. Y'all keep going. I'll keep giving bonus points, but I'll just keep reducing them until I get to 0. Here, what's your, and let's see, today. Okay, let me see what you got. double check that one real quick. Double check that coefficient. Oh, and I want you to multiply it all out.
Oh.
Yeah. Okay, so multiply it all out. That's good, but what's your last name?
That's pretty good though.
There you go.
That way.
Okay. Where are you at? 2. Not sure about this right here.
Okay.
Yeah. And then that, is that 0? Where'd you get 0 from? Not sure where you got 0 from. Go back and look at it. There's some things that are off there. Go back to the problem. There's the, you got it? Yeah, equals 0, and then you distribute everything through. Okay, what's your last name?
Caldera.
Okay. Yep. So I can do 2 more people, that's it, for bonus.
Should come out to this.
There you go. Yep. Yeah. So I mean, like you can keep it in this form. Like that is the equation.
Yeah.
Yeah. But most of the time, like when people look at equations of planes, they get all the constants to one side, all your variables to the other. But yeah, it's good. I didn't reduce this.
Oh,
but yeah.
so it's
Yeah.
great.
I just didn't do that step yet.
Is this better?
Whoa. Yes, that should be 36, I think, though.
36?
Yeah, it should be.
Oh, yeah, because I don't know. Yeah.
Okay. Yep, I got you. I'm going to give you another couple of minutes to see if you can't figure this out. I believe that's the same equation, no? Okay, so this one's saying for you to find the equation of the normal line to the tangent plane. So the previous one was find the tangent plane, right? So when you have a plane, okay, we found the equation of this tangent plane. This is asking to find the equation of the normal line. The normal line is a line that is perpendicular to your plane. All right, so basically, this is asking for the line that's coming out of this plane at the point at which this is tangent to the ellipsoid. See if you can figure that out. I'll give you just like 2 minutes, 3 minutes. That's not for bonus. That's just for see if someone can figure it out. And then I'll answer it in a second. And then I think we're gonna call it a day. Oh, apparently my barbecue grill is in my pool right now. In the yard though. So apparently got really windy at my house. Okay. I always check the weather because, I know things can happen, right? Can't trust it. All right, so let's first, the equation of the plane. That was the bonus one. Did anyone have a question on how to do that? So I only had a few people come up and show me. So what was the equation of the plane? Equation of the plane, not this one, the previous one. 2/3 or negative 2/3? Negative 2/3 x plus 8y plus 2/5 z equals 36. Okay, so that is the equation of the plane that is tangent to that ellipsoid at that point. Hopefully you can get that for the previous example. Now, for the equation of the normal line, just think back to how do we find the equations of lines in this class? What are the two things we need? A point and a direction vector, right? So do we have a point that we can use here? Yeah, the point that's on our tangent plane. So we've got our tangent plane, we've got this point on there, there's the point. So our vector equation of our line will be using this, the couch potato one, right? This is going to be, well, this right here is our point, right? So negative 3, 4, 5. And then plus t times, now we need a direction vector of our line, which we can use what?
You just use the coefficients. Yeah, you use the coefficients.
These numbers right here, negative 2/3, 8 and 2/5, are the normal vector of the plane, aren't they?
Yes.
So the normal vector of the plane comes out of the plane perpendicular to the plane, so that is basically the line, the direction of the line we're looking for. So we just use those negative 2/3, 8, 2/5, and we're there. So you put those together. Okay. All right. This is just a picture of what we just did. And we found the equation of that plane, and we found the vector equation of that line. And that's it. Yeah, so we'll call it a day because apparently my backyard is a disaster right now. And we are officially one entire class period ahead of where we're supposed to be. So that's good because each class period we're supposed to do about 2 sections, so I've freed up quite a bit of time for later. Yeah, so, I mean, yeah, we've got quite a bit. So
everything can be due even later than it was before?
Pardon? What do you mean?
Another 2 days, a week?
For the, well, you mean for the stuff that's due? Well, the problem with that is I believe that there's, at the end of the semester, I believe that I have the 8th mini exam is due the same day as the 7th one. Does that make sense? So, I don't mind pushing anything back, but it's just going to clump up at the back side, if that makes sense.
You just push the 8th one back.
The 8th one till when?
Always on the last day?
Yeah, but our last day of class is actually the same day that grades, I think we end class on a Wednesday. I think grades are due that Thursday night. What's that? Or we could just not do mini exams, right? All right, y'all have a good one.